What is the universe made of? How did it all begin? These questions have captivated humanity for centuries. We look up at the night sky, filled with awe and wonder. The universe is vast and mysterious. It's filled with swirling galaxies, exploding stars, and strange phenomena. But what are the fundamental building blocks of this cosmic tapestry? The quest to unify the laws of physics is not new. Isaac Newton, in the 17th century, unified the heavens and the earth with his law of universal gravitation. He showed that the same force that makes an apple fall to the ground also governs the motion of planets. In the 19th century, James Clerk Maxwell unified electricity and magnetism. His equations described these seemingly different forces as two sides of the same coin, electromagnetism. Newton's laws paved the way for the Industrial Revolution. Maxwell's equations led to the development of radio, television, and countless other technologies. The 20th century witnessed two revolutionary theories in physics: Einstein's general relativity and quantum mechanics. General relativity describes the universe on the largest scales, explaining the motion of planets, stars, and galaxies. Quantum mechanics governs the microscopic world of atoms and subatomic particles. Both theories have been incredibly successful in their respective domains. However, a fundamental problem arises when we try to combine them. The two theories seem fundamentally incompatible. This is where string theory enters the stage. It offers a tantalizing possibility, a way to reconcile the seemingly incompatible worlds of general relativity and quantum mechanics. At the heart of string theory is a radical idea. The fundamental constituents of the universe are not point-like particles, but tiny one-dimensional objects called strings. Different vibrations of these fundamental strings give rise to different particles and forces. String theory proposes that the graviton, the hypothetical particle that mediates gravity, is just one of the many vibrational modes of a closed string. Thus, string theory emerges as a potential bridge between the two pillars of modern physics. String theory, with its grand ambition of unifying the universe, didn't begin with a flash of inspiration about the cosmos. Instead, it emerged from the study of the strong nuclear force. In the 1960s, physicists were grappling with the complexities of this force, which binds protons and neutrons together within the atom's nucleus. Amidst this confusion, a young physicist named Gabriele Veneziano made a remarkable discovery. In 1968, while working at CERN, Veneziano stumbled upon a mathematical formula that seemed to describe the scattering patterns of hadrons with surprising accuracy. Veneziano's discovery sparked a flurry of activity among physicists. Leonard Susskind, Yoichiro Nambu, and Holger Beck-Nielsen independently realized that the formula could be interpreted in a completely new way. They proposed that the strong force wasn't mediated by the exchange of point-like particles, but by tiny, one-dimensional objects, strings. The different scattering patterns observed in experiments could be explained by the different ways these strings could vibrate. This string-based interpretation of the strong force was initially met with both excitement and skepticism. To grasp the essence of string theory, we need to shift our perspective from a universe of point-like particles to one composed of these tiny, vibrating strings. Just as a plucked guitar string vibrates at different frequencies to produce different musical notes, these fundamental strings vibrate in various modes. The different vibrational patterns of these strings, according to string theory, correspond to different types of particles. One particular vibration might manifest as an electron, another as a quark, and yet another as a photon, the particle of light. This idea offers an elegant and potentially unifying picture of the universe. While the idea of vibrating strings offered a compelling new perspective on particles and forces, Early string theory faced a significant hurdle. It required the existence of extra spatial dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions weren't merely a mathematical quirk, they were essential for the internal consistency of the theory. String theory proposed that these dimensions are curled up or compactified to such small sizes that they are not directly observable at our everyday scales. The 3 spatial dimensions we perceive could be part of a larger, higher dimensional reality, with the extra dimensions so tightly curled up that they are invisible to current experiments. At the heart of string theory lies a simple yet profound shift in perspective. The fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional objects called strings. Just as a guitar string, when plucked, vibrates at different frequencies to produce different musical notes, these fundamental strings also vibrate in various modes. Each vibrational pattern, according to string theory, corresponds to a different kind of particle. Think of the universe as a grand cosmic symphony. The strings, with their endless dance of vibrations, are the fundamental instruments. String theory, while offering an elegant way to describe particles and forces, comes with a rather mind-bending requirement: the existence of extra spatial dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions are not merely a mathematical artifact of the theory, they are essential for its internal consistency. String theory proposes that these extra dimensions are curled up or compactified to such incredibly small sizes that they are not directly observable at our everyday scales. These hidden dimensions, though unseen, would play a crucial role in shaping the fundamental properties of particles and forces. String theory, in its quest to unify the forces of nature, often incorporates a concept known as supersymmetry. This elegant idea proposes a fundamental symmetry between 2 basic types of particles that make up the universe: fermions and bosons. Fermions are the building blocks of matter, such as electrons and quarks. Bosons, on the other hand, are the force carriers, mediating interactions between particles. Supersymmetry suggests that for every known fermion, there exists a corresponding supersymmetric partner that is a boson, and vice versa. However, despite decades of searching, experimental evidence for supersymmetry remains elusive. String theory, in its most basic form, postulates that the universe is made up of tiny, vibrating strings. But these strings are not all created equal. They come in 2 main varieties: open strings and closed strings. Open strings have 2 distinct endpoints. Closed strings form continuous loops with no endpoints. Closed strings are particularly significant because one of their vibrational modes corresponds to the graviton, the hypothetical particle that mediates the force of gravity. Open strings are associated with other forces and particles, contributing to the rich tapestry of our universe. As we delve deeper into the world of string theory, we encounter objects even more exotic than the strings themselves: brains. These objects are higher dimensional surfaces that extend throughout space-time. While strings are one-dimensional, brains can have various dimensions. A 2-brain is like a 2-dimensional sheet, while a 3-brain is a 3-dimensional volume. Our entire universe might reside on a gigantic 3-brain floating within a higher dimensional space. Open strings can have their endpoints attached to brains, giving rise to a rich variety of physical phenomena. The concept of brains also opens up intriguing possibilities for cosmology, such as the idea that our universe might be just one of many brains floating within a higher dimensional multiverse. By the early 1990s, string theory had blossomed into a vibrant but somewhat chaotic field. Physicists had developed 5 distinct versions of the theory. Then, in 1995, Edward Witten proposed a radical new idea. He called this unifying framework M-theory. M-theory operates in 11 dimensions. The 5 string theories could be related through dualities. M-theory hinted at a deeper level of unity and elegance in the universe's fundamental laws. M-theory, in addition to unifying the various string theories, brought with it a new cast of characters. Branes. Branes, unlike strings, which are one-dimensional, are extended objects with two or more dimensions. Imagine a thin sheet of paper. That's a two-brane. In M-theory, branes can exist with up to 9 spatial dimensions, moving within the full 11-dimensional space-time. Our universe might reside on a gigantic 3-brane, like a vast island floating within a higher dimensional space. String theory, with its requirement of extra dimensions, leads to a mind-boggling possibility: the existence of a multiverse. Imagine our universe, not as the sole cosmic entity, but as one bubble in a vast cosmic foam. Each bubble represents a separate universe, potentially with its own unique set of physical laws and constants. How does this arise from string theory? Recall that string theory requires extra spatial dimensions beyond the 3 we experience. These extra dimensions, according to the theory, are curled up or compactified into tiny shapes. However, there are many different ways to compactify these extra dimensions, each leading to a different set of physical laws in the resulting 4-dimensional space-time. Think of it like baking a cake. The basic ingredients, like flour, sugar, and eggs, represent the fundamental constants and laws of nature. However, depending on how you combine these ingredients, the recipe, you can end up with vastly different cakes: chocolate cake, vanilla cake, sponge cake, and so on. Similarly, in string theory, the way you compactify the extra dimensions is like choosing a different recipe. Each compactification scheme leads to a different universe with its own unique flavor of physics. This vast landscape of possibilities is often referred to as the string landscape. The string landscape, with its potentially vast number of universes, raises a profound question. Why do we find ourselves in this particular universe with its specific set of physical laws that allow for stars, planets, and life as we know it? This question has puzzled physicists and cosmologists for decades. One possible answer lies in the anthropic principle, a philosophical consideration that suggests our existence as observers might play a role in explaining the properties of the universe we observe. The weak anthropic principle, for example, simply states that we observe this universe because it has the properties necessary for observers like us to exist. In other words, if the universe were significantly different, with different fundamental constants or laws, we wouldn't be here to ponder its mysteries. The strong anthropic principle goes further, suggesting that the universe must have properties that allow for life to emerge at some point. The anthropic principle, while intriguing, remains controversial. Some physicists see it as a tautological statement, providing little explanatory power. Others view it as a necessary consideration when confronting the vastness of the string landscape, a way to make sense of our place in a potentially infinite multiverse. String theory, for all its elegance and promise, faces a significant hurdle: a lack of direct experimental evidence. Testing string theory directly would require an accelerator the size of our galaxy. This experimental inaccessibility has led some critics to question its scientific validity. Without empirical grounding, string theory risks veering into untestable speculation. Proponents argue its mathematical consistency and potential to unify gravity and quantum mechanics. They highlight advances like the holographic principle and new perspectives on black hole thermodynamics. Our journey into the heart of string theory has taken us to the very edge of human understanding. We've explored the idea that our universe might be composed of tiny vibrating strings. We've delved into extra dimensions, hidden from our everyday perception, and we've contemplated a vast multiverse, a cosmic tapestry woven from countless universes. String theory offers a glimpse into a deeper level of reality. It holds the promise of unifying the fundamental forces of nature. Yet, for all its allure, string theory remains an unfinished symphony. It faces significant challenges, notably the lack of direct experimental evidence. Despite these challenges, the quest to understand string theory continues. The journey is far from over. It is driven by humanity's insatiable curiosity to unravel the mysteries of the universe.
Sun is shining.